So we have planned today to discuss two important inequalities. Everyone knows one inequality, there is Cauchy-Schwarz inequality, and another inequality we have also discussed and proved, that is called Holder's inequality. The interesting thing is that we have applied Cauchy-Schwarz inequality in many problems, many areas, and today we again would like to explore these inequalities in a very critical way. Also, we will discuss a problem where this just application, a simple application of this inequality will not be enough to solve this problem. Along with that, we might need some more results or more knowledge on measure theory in order to get the final solution or the final proof. So we are going to discuss everything with respect to a few problems, few specific problems that we are going to discuss, which will use this Holder's inequality, Cauchy-Schwarz inequality, and some other concepts of measure theory that we have learned, but not very difficult, very easy. But we have to apply the things, all these things, appropriately in towards solving these problems. Today we will discuss a few problems which will be solved using Cauchy-Schwarz inequality and Holder's inequality. The two very famous inequality, and that are very frequently used in probability, measure theory, and many other areas in mathematics and statistics. The first problem goes like this. It's a very interesting problem. Let us define a function f, which is a non-negative, that means f greater than equals to 0, and it is measurable on closed interval 0 1, and integral over 0 1 closed interval f square d mu equals to integration over the same interval f cube d mu equals to integration over 0 to 1 closed interval f4 d mu, and they are less than infinity. Then all we have to show that f equals to f square almost everywhere. It's a very nice looking problem, and the result is looks obvious, but let us see how we can prove it. The first we apply Cauchy-Schwarz inequality to have integration over 0 to 1 closed interval f cube d mu equals to integration over 0 to 0 1 f into f square. So we split this f cube, we can treat this as product of two functions, one is f and another is f square, so that we can directly apply Cauchy-Schwarz inequality, and this gives us that the integral f cube d mu is less than equals to integral f square d mu to the power half into integral f to the power 4 d mu whole to the power half. Now whenever I say integral or integration, it means for this problem that integration is always between 0 to 1 closed interval. Now this quantity gives us integration just f square d mu. Why? Because the second term, integration f4 d mu, is nothing but integration f square d mu by the given condition. So it becomes integration f square d mu whole to the power half into integration f square d mu whole to the power half, that becomes integration f square d mu. Let's call this as equation 1. So in equation 1 says that integration f cube d mu is less than or equals to integration f square d mu. Now if we use the given condition in 1, because this integration f cube d mu is equals to integration f square d mu by the given condition, and by Cauchy-Schwarz inequality it is less than equals to, so naturally this can happen only if the equality case of Cauchy-Schwarz inequality is true. That means in this case we get an inequality situation in Cauchy-Schwarz inequality, which is a very natural one given the problem. But as soon as we get the equality in Cauchy-Schwarz inequality, if we recall that when does this equality happens in Cauchy-Schwarz inequality, we see that this is possible if only the two functions that are involved, in this case f and f square, they are proportional to each other. That is, we can write a into f equals to b into f square almost everywhere, but some a and b belongs to the real line. So this is a very interesting situation. Very naturally we get an equality situation, and from there the condition for that equality in Cauchy-Schwarz inequality tells us af equals to bf square almost everywhere. Now from the given condition again, if we think that if we just take integral on both sides, that means a into integral f d mu over, of course, 0 to 1 closed interval, then integration f d mu is nothing but integration f squared d mu. So this becomes a into integration f squared d mu. And again we know that a into integration f d mu is nothing but b into integration f squared d mu. So this automatically gives us that a must be equals to b, which implies that f squared, that means what we get is in this quantity, we get that f equals to f squared almost everywhere, because integration f d mu is less than infinity. That means we can immediately write, since integration f d mu is less than infinity, we can write integration, taking this quantity on the left side, we can write an a equals to b. So we are left with integration f d mu equals to this quantity, integration f squared d mu. That means integration, we can bring this on the left side, integration f minus f squared d mu equals to 0, or the other way around. So this automatically means that f equals to f squared, almost surely. Now one interesting point to note, that it can be easily shown that if f equals to f squared almost surely, then f will take probably only two values, 0 or 1. That means f is basically an indicator function. So that is kind of byproduct of this result, that under this problem f is nothing but an indicator function over 0, 1 interval. Now the second one, slightly more complicated but not a very difficult thing, a difficult one. Let the function f be measurable, again on the closed interval 0, 1, and for 1 less than equals to p less than infinity, we define gp equals to integration 0 to 1 mod fx to the power p dx whole to the power 1 by p. Then show that g is non-decreasing on 1 to infinity. That is very important. So first consider two quantities p and q such that p is less than q. Then we apply the famous Holder's inequality to get integration 0 to 1 mod fx to the power p into 1 dx. That means there are two quantities, and applying Holder's inequality on these two quantities like u and v, where u is mod fx to the power p and v is 1, we have integration 0 to 1 mod of fx to the power p whole to the power q by p dx, the whole thing to the power p by q. That is kind of norm. And into integration 0 to 1 1 to the power q naught dx whole to the power 1 by q naught, which immediately gives us just the first quantity, that is integral 0 to 1 mod fx to the power q dx whole to the power p by q. Now what is q naught? Q naught is nothing but satisfying the conditions of Holder's inequality. If we write this as 1 by q by p plus 1 by q naught equals to 1. So that is the condition for Holder's inequality. That means q naught is nothing but q by q minus p. Just a little bit of simplification will give us this value of q naught. Now q naught is nothing but the exponent conjugate of q by p in order to satisfy Holder's inequality. So from 1, if we raise both sides of 1 to the power 1 by p, all we have is integration 0 to 1 mod of fx to the power p dx whole to the power 1 by p less than equals to integration 0 to 1 mod of fx whole to the power q dx whole to the power 1 by p. That means what we are doing is just raising the power to the power 1 by p. Now if we raise to the power 1 by p, the right side becomes 1 by q, because the right side of 1 has the power p by q. So if we raise to the power 1 by p, then p by q into 1 by p becomes 1 by q. That's what is here exactly. So this is nothing but, now the left hand side is nothing but gp and the right hand side is nothing but gq. So what is this? gp is less than equals to gq. For p less than q, we have already assumed p is less than q. And what is p basically? P is greater than or equals to 1. That means q is always greater than 1. So this indicates that gp is a non-decreasing function in p when p belongs to 1 to infinity, one side is closed. Because p is greater than equals to 1, that's the value of p we have started. And q is greater than p. So the entire range would be 1 to infinity, 1 closed. So that's the proof. Let us consider another one, two small problems. So let us again consider p greater than 1 and f belongs to the LP space, LP over closed interval -1 to 1. Then show that f will belong to, or f must belong to L1 over -1 to 1, the same closed interval. Again, take two numbers p and q such that 1 by p plus 1 by q equals to 1. Now, one interesting thing is that whenever there is LP means the pth mean. That means it gives us, immediately it gives us the idea, or our thought process will be automatically linked with some kind of norm or pth norm. Or whenever we have some kind of pth norm or LP, again, Holder's inequality is a very, very standard result to apply and to see whether we can get anything out of it, or we can get the result, in fact. So, and in order to apply Holder's inequality, we have to consider two numbers p and q such that 1 by p plus 1 by q equals to 1. Again, just straight away apply Holder's inequality. Let's see what happens. So integral over -1 to 1 closed interval mod of f into 1 d mu is less. That means we are writing mod of f as product of two functions. One is mod f, another is 1. Is less than equals to, just by applying Holder's inequality, integral over -1 to 1 mod of f to the power p d mu whole to the power 1 by p into integral of -1 to 1 to the power q d mu whole to the power 1 by q. Now again, we can immediately see that this entire thing becomes, so from the second term on the right side, this is nothing but 2 to the power 1 by q, because this integral is nothing but just 2, so 2 whole to the power 1 by q, and the first term is nothing but the pth norm of f, so pth norm of f, and this is of course less than infinity. It is the given condition. So what we have, the proof is there, the proof is complete. So that's what we are supposed to prove. So we started with L1 norm and we move on to pth norm using Holder's inequality, and we show that this is finite or less than infinity, because it's given that the pth norm is, that means this belongs to, actually f belongs to LP. So this automatically implies f belongs to L1. That completes the proof. And the last one in this line is, suppose p greater than 1, and again the same kind of problem, f belongs to LP over -1 to 1 closed interval, and also consider another interval in, which is an open interval -1 by n to 1 by n. That means open interval -1 by n comma 1 by n. And let us take a value of beta as p minus 1 by p. We have taken p as greater than 1, so p minus 1 is positive, and hence beta is always positive. In fact, beta, so p minus 1 is less than p, so in fact beta lies between 0 and 1. All we have to show is that limit n goes to infinity, n to the power beta, integral over in mod of f d mu equals to 0. This is very interesting, because integral over in, and in is kind of an open interval lying between, that means -1 by n to 1 by n, and this actually is shrinking towards 0, because as n goes to infinity, this open interval ultimately will contain only one value, 0. That we are going to see immediately in the proof. So how to prove this result? Again, start with two numbers p and q such that 1 by p plus 1 by q equals to 1, and this implies in this case that if you just see what is the value of q, or rather we can immediately see that this beta is equals to 1 by q, because if we simplify, this becomes 1 by q equals to 1 minus 1 by p, that is p minus 1 by p, which is nothing but beta. So this immediately gives us beta is 1 by q. Again, apply Holder's inequality, we get integral over in, this is important, integral over in mod f into 1 d mu, the same old technique that we have used in the last two problems, less than equals to, by Holder's inequality, less than equals to integration over in mod of f to the power p d mu whole to the power 1 by p into integral over in 1 to the power q d mu whole to the power 1 by q. Now integral over in of 1 to the power q means 1 d mu. Now in is minus 1 to minus 1 by n to 1 by n. This integral gives us the value of just 2 by n. So 2 by n whole to the power 1 by q. Now 1 by q is beta. So this second term is exactly equals to 2 by n whole to the power beta. And what is the first term? It is nothing but the norm of f to the power p, which is less than infinity. Now, or rather, we can keep this thing as it is. So integral over in mod of f to the power p d mu whole to the power 1 by v is better to write this way. Okay, so what we get immediately, just by transposing, so n to the power beta into integral of mod f d mu over in is less than equals to 2 to the power beta into integral over in of mod of f to the power p d mu whole to the power 1 by p. Let's call this as equation 1. Then we must have n to the power beta integration of mod f d mu over in is less than equals to 2 to the power beta integration over in mod f to the power p d mu whole to the power 1 by p. The same equation I have written once again. We can change it. Now recall one interesting thing. Nu e, what is nu e? If we define nu e as integration over e mod of f to the power p d mu, we can show that this is nothing but a measure on the closed interval minus 1 to 1. And it is also a finite measure, because if we take nu of minus 1 to 1 closed interval, this means it is equals to integration, instead of e we write minus 1 to 1 closed interval mod of f to the power p d mu, which is less than infinity. That means it's a finite measure. Nu e itself is a finite measure given in terms of integral with respect to d mu, with respect to mu, the another measure mu. Hence, by continuity of measure, since it is a measure, we can apply the continuity theorem for measure, which gives us integration over in mod of f to the power p d mu, which is nothing but nu of in, because here e is nothing but in. Now nu of in converges to nu of intersection in, because in is a sequence of decreasing sequence of intervals, decreasing sets. So in the limit, it will go to the limit of intersection of n equals to 1 to infinity. Now if we recall what is in is the interval minus 1 to minus 1 by n to 1 by n open interval. So it will always contain 0. So in the limit, so as n goes to infinity, the length of the interval gets smaller and smaller. So as a limit, it will contain only the value 0. So nu of intersection in n equals to 1 to infinity will be equals to nu of only a singleton set, that is 0. Now if I write what is nu of a set is integration over that set, in this case it is a singleton set which is 0, mod of f to the power p d mu, and naturally this integral is exactly equals to 0. So by applying 2, so let's call this equation as 2. So applying 2 in 1, because 1 is this. So that means this right hand side quantity is actually 0. That means the result will follow immediately. So although we have applied, this is a very interesting problem, we have applied Holder's inequality, then we have to consider the idea of measure and in fact the finite measure, and we need another important theorem, that is the continuity of measure, and that will ultimately help us to prove this nice result. So we have already seen that we have discussed a few problems that are nothing but the direct application of Cauchy-Schwarz inequality and Holder's inequality. But the most critical thing or the beauty in one problem is that usually we apply Cauchy-Schwarz inequality, as we look this thing as an inequality, and sometimes we don't really remember under what condition equality can happen. Equality holds. So one problem, actually the entire problem is solved based on the conditions when the equality holds in Cauchy-Schwarz inequality. So that gives us another that actually opens another area of understanding, that whenever we have any inequality, we must check or we must be sure about the condition under which the equality sign holds. This actually sometimes carry extremely important information, and without which an inequality cannot be complete. And if we can show for some reason that there is no such condition under which equality holds, then we should write just strict inequality. But that means whenever there is an inequality and whenever there is less than equals to or greater than equals to, we should be very, very careful, and we should know that under what conditions this equality holds. Actually, and again, we have seen that application of not only Holder's inequality would be enough, but we need some extra knowledge on measure theory, as for example, continuity of measure in one problem we have seen probably in the last problem. And that finally gives us the final result. And not only continuity of result, but continuity, and then we are considering the limit value, of course, as a consequence of continuity theorem. So the only one message I would like to convey to all of you, and of course to all of us also, that not only application of not only one single theorem is enough to solve a problem. We know all these theorems, we know all these results, we know the concepts, measure theory, continuity theorem, and other dominator convergence theorem, monotone convergence theorem, several inequalities we have, Fatou's lemma, Borel-Cantor lemma. But given a problem, we need to understand what result we are going to apply and when we are going to apply. Now, when we apply a particular result, be very, very careful to check the conditions under which we are actually permitted to apply this result. So that's the most important message that I would like to convey.